as your second to last homework assignment. This one is a little bit, somewhat late, but it's not too bad. And then the one, there we go. Then the one due next week is shorter, so that you have a little bit of time to get started preparing for finals next week. I didn't put it on this slide, but I'll just mention, since it's a couple weeks away, our final exam is at 7:30 in the morning. Everybody remember that? It's a little rough. It's on Wednesday, May 6th at 7:30 in the morning. I will remind you a bunch of times about that before we get to it. So everybody knows. I also didn't put it on this slide, but we have a review session on the Friday prior to the final exam. So that is May 1st, Friday, May 1st. So there's a review session in the Marshall Student Center. And I will, what's up? I'm sorry? At what time? I believe it is, yeah, it's 10 to 12 that Friday. I'll send out the information soon. So I'll send it out sometime either later this week or early next week about the review session. The review session will be recorded though, so if you can't make it for that time, I'll send out the recording as well. Okay, so today we're going to talk a little bit about optical instruments, and then things are going to get weird when we start talking about relativity. I think all of you, yes. Yes, I will post the practice final exam next week to give you, give you some time, give you an additional resource to help prepare for the final exam. What I was going to say about relativity, before we get to talking about optical instruments for a little bit, is that so far in physics, we've done everything in the kind of classical physics way. So classical physics is usually described as the physics described by Newton, right? Where you exert a force on something and then that object accelerates, right? I watch a car going by, I can measure its speed and its velocity, right? And no matter where you are, if you're the person standing on the side or if you're a person riding in that car, everybody agrees on time, everybody agrees on space, and all sorts of things like that. Well, we're going to break that with relativity. And I think that all of you probably heard of Albert Einstein, right? So this is Einstein's theory of relativity that we're going to start on today. All right, but before we get to that, we need to go back and talk about some of the things that we can do with lenses and mirrors. And so at the very end of class last week, what? I don't even know how to select that. Okay. Stem launcher isn't responding. Okay, that's weird. I'm not sure. I've never seen that message before. Have you guys seen that message before? I haven't seen it before.
No.
All right. So last time we said that a camera can focus an image on a detector by changing the lens detector distance. So there is in nice digital cameras, you have a lens that is mounted on the front of the camera, there's a detector at the back. When you focus the lens or when you make adjustments to the lens, you're changing the lens detector distance, and that's what's focusing an image on that detector. Your phone actually does have a slight amount of ability to adjust the distance of the lens from the detector in your phone. Some phones do that. I think most phones do that, but it's just a very small difference. There is a lens in the front of the camera on your phone. So this lens is able to, I believe, change distance by just a little bit on your phone. A human eye, though, focuses an image on the retina by changing the shape and thus the focal length of the lens in the eye. So there's contraction or expansion within your eye that's changing the shape of the lens. And so rather than changing the distance of your cornea or the lens in your eye from the front of, or from the back of your eye, you're changing the shape of the lens. So you're changing the focal length, right? And so I gave you the example last time that if you hold out your hand in front of you, you can focus on your hand, but then you can also focus on me, and those are two objects at different distances, and what's going on is your eye is change the shape of the lens in your eye. Okay, so we can also use lenses or mirrors to build things like a compound microscope, or microscopes, and refracting telescopes. So we can use lenses to build these devices. And these allow us to magnify an image of something in the distance or nearby. So let me give you an example, first of all, of the optical setup for a compound microscope. Excuse me. All right, so we got two lenses in the compound microscope. There is what's called the objective lens, that's the one on the left in this diagram, and then there is the eyepiece lens, the one over on the right. Okay, so this is the essential setup of a compound microscope. I think many of you probably use this in a biology lab. So we have some object that's very small. We place it just outside of the focal point of the objective lens. So that's FO here on the left. And the rays traveling through that first objective lens produce a real image over here along this dashed line, which is the optical axis. So the real image is that dashed line of the ant, right, at that position. And then that real image, those rays from the real image, continue through the eyepiece lens, and because the real image is inside the focal point of the eyepiece lens, it produces a virtual image of the ant that is considerably larger than the actual object, right? So this virtual image, right, is a virtual image because the rays that appear to come from this virtual image do not actually pass through that location, right? So the only thing I would change about this diagram is I would make the rays coming from the head of the virtual image dashed instead of solid, right? Because those are not actual light rays, right? They just appear to be coming from that location, but they're really coming from the real image and going through the eyepiece. Okay, so you have an objective lens and you have an eyepiece lens, and together they're producing this significantly magnified image of an object that is close to the focal point of my objective lens. All right, so that's how the compound microscope works. And then I think in lab, maybe you had compound microscopes that have different eyepieces, right? You can rotate the eyepieces so that you get different magnifications, right? So if you have a different eyepiece with a different focal length, then you're going to get a different magnification. So that's what you're able to do. All right, for a refracting telescope, it's a little bit different. You use two lenses, and they're both converging lenses in both cases. The compound microscope and the refracting telescope both use converging lenses. But with a refracting telescope, you have an objective lens and an eyepiece lens, just like you did before, except that now the object is not inside the focal point of the objective lens. The object is essentially infinitely far away, very, very far away, like a star or a galaxy or a planet even, right? So it's very, very far away, so the rays of light coming into my objective lens are essentially parallel, right? And so when they travel through the objective lens, the essentially parallel rays coming in are going to focus at the focal point of the objective lens. And so that's going to produce a real inverted image at the focal point. And then the eyepiece lens converges those rays again, so that it produces a virtual inverted image at infinity, which is also magnified. All right, and I have diagrammed this specifically on this, or I produced this diagram specifically where you actually have dashed lines for the lines that are not the radius along which the light rays are traveling. But also I've given you a thin objective lens and a thicker eyepiece lens. And that's to try to indicate that I have a longer focal length for the objective, and I have a shorter focal length for the eyepiece. And that's important. That's in part why most refracting telescopes come in fairly long tubes, because you have to have a long enough objective lens in order to get a magnified image of the object and have a short eyepiece focal length. Right? All right. So so you have to and then the objective lens and the eyepiece lens have to be separated by the sum of their focal lengths in order for you to get a nice focused image. So one other thing about this, we mentioned before that when you pass light through a lens, you have two issues that you have to deal with. You have spherical aberration, right? So you have different focal points for different pathways through the lens. So that's number one. And the way that we got around that was by using a very thin lens, right? So that's not so much a problem for the objective lens. It's a little bit more of a problem for the eyepiece lens. But you can use relatively longer focal lengths to get around that so that you're using less of the entire sphere, just a small portion of the sphere. But the other problem that you have is chromatic aberration, right? Different colors are going to pass through the lens at slightly different directions due to the dispersion within within the objective lens, and then dispersion again within the eyepiece lens. And that you can't completely get around. You can use a material for your lenses that has very low dispersion, but that's still an issue. So it's not ideal to build a refracting telescope in order to do your research, for instance, if you're an astronomer. And one more factor to that. With the eyepiece lens, the objective lens and the eyepiece lens for the microscope, it's not a problem because you can build those and have them be fairly small within the laboratory because you can light up your, whatever, you can shine some light on the object that you're trying to image. For this, you need it to be very dark to be able to see very faint things, and really you need to be able to collect as much light as possible. So your objective lens actually needs to be very large. And so that causes a problem because the larger I make my objective lens, the shallower the curve has to be on the lens. And also then I have to support the lens around the edge, and it's made of glass. And the edge is the thinnest part. So it gets very difficult to build a very large lens. And so there's kind of a limit to how big you can build these. And the bigger I build my lens, the longer my tube has to be, right? And so that's a problem, which we can get around with reflecting telescopes, which we're going to get to in just a second. But first we're going to take a look at compound microscope magnification, or total magnification. Because it's not one lens, it's two lenses, so there's two different focal lengths. So total magnification, we're going to call capital M. So first you have the magnification of the objective, of the objective lens. And that's equal to the same magnification we've had before, minus DI over DO, minus the image distance over the object distance. But we're putting the object very close to the objective lens, so DO is approximately equal to the focal length of the objective lens. So the magnification of the objective lens is basically equal to minus DI over FO. Right? The total magnification, capital M, is MO times ME, where ME is magnification of the eyepiece. The magnification of the eyepiece is 25 centimeters, and we'll talk about why we're using 25 centimeters over the focal length of the eyepiece. 25 centimeters is essentially the near point for regular human vision if you don't have any kind of difficulty seeing either near or far, right? So 25 centimeters is a little bit less than a foot. So if you put your hand a little bit less than 1 foot in front of your face, you should be able to focus on it. I can't quite get it. I can get just a little bit more than a foot in front of my face, but you can focus at that distance. If you bring it inside that distance, you're going to have trouble focusing your eye at that distance. right? You will not be able to focus on your hand if you bring it closer to you by a lot. You know, eventually, at some point, you will not be able to focus on your hands. Okay, so that's the near point for human vision, and then this is the eyepiece. Okay, so that's where the image has to be. It has to be that far away in order for you to focus on it. And then we're divided by the eyepiece focal length because that's essentially where we want to have our object. Or really the real image produced by the objective lens. So the total magnification, then, if we do substitution, this and this together becomes minus 25 centimeters times the image distance, di, divided by FO times FV. All right. So the upshot of this is that we want the objective focal length and the eyepiece focal length to be very short. Right? Because that's going to, if I have a small number in the denominator of this fraction, then that's going to give me a large magnification. And so di has to be approximately the barrel length of the microscope. So the lenses that you have in the microscope that are near the object you're trying to image and near your eye, they actually have very short focal lengths. But then the distance between those lenses is approximately the image distance, the barrel length of the microscope. Okay. For refracting telescopes, so this is a specific Keplerian design. It's a lot easier to calculate. Kepler is just minus FO divided by FE minus the focal length of the objective lens divided by the focal length of the eyepiece lens. And so you can see why we, have trouble building a large diameter lens refracting telescope. Because remember, if I build a big diameter lens, that's how I'm going to collect a lot of light and be able to image something that's very, very dim off in the distance. But the larger I make that diameter of the lens, well, I have to make it thin enough so that I don't have the spherical aberration and chromatic aberration issues that I'm trying to get around, right? So if I make something very large in diameter but very thin, that's difficult to build. And even so, again, I'm supporting a round edge of the telescope, so that's problematic. And there's a limit to how big you can build that type of optical instrument. So we're actually not that interested in the magnification being very large in astronomy. We're more interested in how much light can you collect, because that's more of an issue. You can always increase the magnification by making your eyepiece focal length very, very short. No problem. Make FE very small, you can make the magnification very large. But it's more of an issue with the more serious concern in astronomy is how much light can you collect. So you want to make a very large very large lens, or potentially very large mirror. So this is the design for a refracting telescope. And I'll also point out that the image that you see is inverted. So if you look through a refracting telescope, you see something upside down. But like we said, making a very large objective lens is very difficult, and then you have to have a nice, rigid tube that is very, very long. So instead, an easier way of doing this is to have a reflecting telescope, where you use mirrors instead of lenses. Now, there's a couple different advantages to the mirrors. The mirrors do not have to be supported around just their edges. You can support the mirror on the back, which is fine, because that's the light is not traveling through the back of the mirror, right? So that's number one advantage. The second advantage is that they don't suffer from chromatic aberration, right? When the light passes through a lens, different colors are going to travel along slightly different paths because of dispersion. But with a mirror, you always have angle of incidence is equal to angle of reflection, regardless of the wavelength or color of the light. So you don't have any chromatic aberration, and you don't have to worry about supporting it around the edge. Instead, you can support it on the back. So that's nice, right? The other thing that you can do is you can place a secondary mirror like this, the convex hyperbolic secondary mirror, in front of your primary mirror, and have the light reflect back down through a hole in the center of your primary mirror to your detector, camera, or spectrometer, right? And that allows you to fold the focal length. So I don't need a super, super long tube where the lens has to be on one end and then the eyepiece lens has to be on the other end of the tube, right? There's no simple way to do that with a refracting telescope. But with a reflecting telescope, you can, so that shortens your tube by quite a bit. Now, it means that the secondary mirror is blocking a little bit of the primary mirror, but that's not an issue. You can still see an image of the object. It's very, very far away when these parallel light rays come in. So the other thing, right, is we still would suffer from spherical aberration. So I think we said previously that one of the ways to get a better image is to not use a spherical mirror. And this design uses hyperbolic mirrors. So this is a Ritchie-Chrétien design. This is many research telescopes in astronomy use this Ritchie-Chrétien design. This is the two guys who came up with this design. And so they use a concave hyperbolic primary mirror. So that converges the light. And then a convex hyperbolic secondary mirror. So I know that the light rays do come together at F here, this focal point behind the primary mirror. But that's still causing them to diverge a little bit from the path that they were on, traveling to this convex hyperbolic secondary mirror, because this convex hyperbolic secondary mirror is a diverging mirror, right? The light rays that are coming towards that mirror are going to spread out a little bit. And so they're just spreading out a little bit compared to what they were doing coming from the concave hyperbolic primary. Okay, so let me show you an example of this. This is just a diagram to show you the optical path of light. Here is a reflecting telescope. So the big image is a computer-generated image, and then the one down here on the bottom left, I took a screenshot last week of their webcam. They're currently building this telescope in Chile. This telescope is called the ELT. The ELT stands for the Extremely Large Telescope. I know that's just kind of comical and silly. But that is literally what it's called, the Extremely Large Telescope. It's being built by the European Southern Observatory, so it's a consortium of a whole bunch of different European countries. Remember what I said about astronomy, the main thing that you want to do in astronomy, don't care that much about magnification, it's more so about how much light can you collect. So you want a very big primary mirror. The primary mirror on this telescope is 39.3 meters. I don't think it would fit in this room. I think the mirror is larger than this room. Now, it's not a single mirror. It's built out of, and you may be able to see on the edge of the mirror that it doesn't look perfectly smooth. That's because it's built out of a whole bunch of hexagonally tiled mirrors that are mosaic together to make one larger mirror. The other thing is you can see just next to the current status image on the right, they have a truck and 2 people, right? So this is very, very large. So, and it's a little bit, it's not that easy to see in this screenshot of the telescope, but there are a couple trucks and things, and there's a large crane and things like that. So this is a fairly large structure. So this is currently under construction and is supposed to be completed, I believe, either in 2020, I think it's supposed to be completed in 2029. So this will be the largest telescope on Earth when it is complete. Right now, the largest ones that astronomers use are about 11 meters in diameter. And so this is about more than 3 times that in terms terms of its diameter. But mirror size scales as area. So if you triple, or say you triple the mirror size in terms of diameter, then you've increased your light collecting area by a factor of 9. So that's a big deal. And you'll be able to image things in a shorter period of time with this than you'd be able to with just with hours and hours, for instance, on the Hubble Space Telescope, even though it's in space. Okay, so I think that's it for optical instruments. So now we're going to talk about relativity. And to start with, we're going to describe something called an inertial frame and Newtonian relativity. So you studied Newton's laws in Physics 1. And for both of these people, Newton's laws apply in both frames. We have a person who's standing at v is equal to 0 relative to the ground, so the velocity is 0 relative to the ground. And then we have a guy on a bike who's traveling at some constant velocity to the right. And both of these are inertial frames. Newton's laws apply in both frames. Okay, so let's go and write some things down. Newton's first law, I'm sure you all remember. The sum of the forces is equal to 0. Right? Anytime the sum of the forces equal to 0, sum of the forces acting on some object are equal to 0, then that means that the acceleration of that object is 0, which could mean that the velocity is 0, or the velocity is constant. Right? So one of those two things. And each of those different situations describes an inertial frame. All right. And so we used as our example, we have a person standing still with velocity equal to 0 relative to the ground. And then we had a person on a bike. Rather than trying to draw a person on a bike, I'm going to draw a car because it's a little easier to draw a car. And then we have the car traveling to the right. With constant velocity. So both of these are inertial frames. And what that means really is that physics is going to work the same for the person standing here at v is equal to 0 and for the person traveling in the car to the right. So let me give you an example. So the person standing there, let's say that they're holding a ball. They drop the ball. The ball will accelerate towards the ground, and we could use free fall to describe the motion of that ball as the person drops it and it falls to the ground. Okay. Person riding in the car also has a ball, and they drop their ball. Their ball also accelerates to the floor of the car, and it follows the exact same free fall equation as the one for the person who's standing, right? And both of them would agree that the ball accelerating towards the floor of the car or just towards the ground behaves in exactly the same way. So the physics is the same for both of them. However, there's another situation. I'm sorry, my card is boxy like it's the 1970s, but that's just easier to draw. All right, so let's say this, however, we have a car that's traveling at some velocity in this direction, but there's also some acceleration. If the car is accelerating, then this is a non-inertial frame. And Newton's Newton's laws will not be the same for an object in a non-inertial frame. If you're a person in a car that is accelerating and you drop a ball, it will not travel straight to the floor. It will travel along a curved path because of the fact that you're in a non-inertial frame. So we would not be able to use the same laws of motion to describe the ball in the accelerating car. Okay? So that's a difference. So we're going to have to be concerned with the difference between inertial frames versus non-inertial frames in both Newtonian relativity, but then also in what's called special relativity, or Einstein's relativity. Whoops. So the laws of motion are the same in all inertial frames. This is the principle of Newtonian relativity. Or we can state it like this. There's no way to detect absolute motion. Only motion relative to a selected frame of reference can be detected. So let's look back at the examples that we gave. Let's say that this car is passing by this person. The person sees the car traveling in V. Let's say there's a dog in the car. And the dog does not understand Newton's laws, right? So the dog in the car sees the person who is standing traveling away from them at minus v, right? Just velocity in the opposite direction, because that's from the perspective of the dog, right? The dog thinks that the person's moving, and the person would say that the dog in the car is moving. Who's right? Well, it's obviously the person, right? Because the dog's the dumb. No, not because of that. No, neither of them is right, right? We're used to using the reference frame of the ground as our reference frame of rest, okay? But that's just the selected reference frame. Are you currently at rest? Yes and no. If we choose the reference frame of the ground, then yes, you are currently at rest. You're not moving. I don't see anybody running around, okay? But if we choose a different reference frame, then you're not at rest. If we choose the center of the earth, are you at rest? No. You're rotating around the center of the earth. You're traveling in a circle as the earth rotates, right? So you're not at rest relative to the center of the earth. Are you at rest relative to the very center of the solar system, which is the center of mass of the solar system? No. You're orbiting around that point. And the sun actually makes little orbits around that point as well, due to gravitational pull of Jupiter. The center of the mass of the solar system is not inside the sun. So the sun is not exactly the center. It's close, but it's not quite the center. Is the solar system at rest? No. It's making orbits around the Milky Way galaxy once every 220 million years or so. Fun little way to think about that is that when we were on the other side of the galaxy, there were dinosaurs. So in half an orbit around the galaxy, we're more dinosaurs, right? Even less than half an orbit. It's less than a quarter of an orbit around the galaxy, I think. About a quarter of an orbit since we have dinosaurs. Okay, is the galaxy at rest? I could keep going. I could keep doing this for a while, by the way. No, the galaxy's not at rest. It's moving, right? Relative to what? Well, we're actually on a collision course with the Andromeda galaxy, the next nearest large galaxy to us. Maybe, probably, 50% chance. I sell galaxy collision insurance if you'd like. You can pay me 1 cent for every year until the galaxies collide. Very little rates, except you gotta pay up front. That's billions of years, by the way, so you'd be paying me millions of dollars. So don't worry about it. You're not gonna be it. All right. But in any case, every time we ask this question, are you at rest? Is this at rest? Is something else at rest? We're always having to say relative to what, right? Relative to what reference frame. So you're always picking an origin, right? You're picking some point in space, and then you're saying, are you moving relative to that point in space? If we choose the ground, then no, you're not moving. You're at rest. But if we choose some other reference point, then you are moving. Okay. Now, it's pretty simple in Newtonian physics to translate between reference frames. We use the Galilean transformation. Between inertial frames. All right, and the Galilean inertial frame, or excuse me, Galilean transformation between inertial frames. Oh, before I write X, Y, and Z, let me draw some inertial frames. So, here's X, here's Y, and here's Z. So this is a three-dimensional coordinate system, right? You have three spatial dimensions. All right, then let's say that there is the car, that's you at rest in your seat. And then let's say that there is a person on a bike or a car that is traveling past you. And we're going to call their reference frame the prime reference frame, or the little apostrophe after this. Okay. And so that is X prime, Y prime, and Z prime. But this reference frame has a velocity, v, along the x direction relative to the other reference frame. And so x prime can be described, so positioned within this prime frame in the x position can be described as x minus v times t. Okay, so because it's traveling, because this second reference frame is traveling in the positive x direction, that means that 0 in this reference frame is at some positive x in the non-moving reference frame. Okay? Right, so at some time t, right, this reference frame has slid to the right, so 0 is to the right of where 0 is in x, y, z, so you would need some positive value x minus v times t to get you back to 0 in x prime. Y prime is just y, it's the same, and z prime is equal to z. And then also, t prime is also equal to t, so time is the same in both of these inertial frames. You can also do a transformation, not just of position and time, but also velocity. So Vx prime is equal to Vx minus V. Vy prime is equal to Vy. And Vz prime is equal to Vz. So let me just describe what we're talking about when we say Vx prime versus Vx. So Vx is the velocity in this first reference frame of some object. Not the velocity of the reference frames, but the velocity of some object. So remember what I told you about how if you are standing there and you drop a ball, right, and then it accelerates down towards the ground. We're talking about the velocity of the ball. So let's say the velocity of the ball is downwards, right? Only in the y direction, right? So only in the y direction. So it's not affected by this transformation because the person who, say, is in the car traveling by, they watch you drop the ball, they see it travel straight down as well. Okay? Or they are measuring, they're not measuring any velocity of the ball in the x direction. They're only measuring the velocity of the ball in the y direction. But if you, the person who's standing, and throw a ball, say, to the right, and the person in the car is traveling along with the same speed as that ball, they will see the ball as being stationary. Now, I know that the ball is actually going to follow a parabolic path as the ball towards the ground, but let's say you throw it fast enough that it travels for just a short period of time, approximately horizontally. So they're going to see the ball basically just kind of floating stationary through the air if the ball is traveling at exactly the same speed as the car. So let me show you an example of that, actually. If you have things that are traveling at the same velocity in an inertial frame, or traveling at a velocity that is the exact opposite as the velocity of your inertial frame, then you're basically at rest. And they tested this at much lower speeds. Here, hold on just a second, I'm trying to sound out. They tested this at much lower speeds before they did this at 80 kilometers an hour. So they're in a truck, and there's a guy in this chair, and 80 kilometers per hour is, it's not quite 50 miles an hour. I think it's about 50 miles an hour. Yeah. And they're going to shoot him off the back of the truck.
Okay, that's final speed?
So he's wearing a helmet because, of course, this is somewhat dangerous, but if you fire somebody off the back of the truck at the same speed that the truck is traveling, then he's just dropping straight down in the reference frame of the ground, right? So he's traveling in an inertial frame on the truck at 80 kilometers per hour, but then this catapult thing fires him at 80 kilometers per hour in the opposite direction, and so he's just at rest in the reference frame of the ground when he falls to the ground. Anyway, I saw this. I saw this happen. They did this recently, and then I saw it, and I was like, all right, I need to use this in class. When did they do this? This was like, I don't have the date, 2 months ago. Anyway, so in any case, that's Newtonian or Galilean transformation, right? So let's go back to the notes. So in that case, so he's the object traveling at some velocity, right? He's in this prime reference frame, the guy that's getting fired off the back of the truck, okay? The prime reference frame is traveling at 80 kilometers per hour, right? So it's traveling at 80 kilometers per hour, and his velocity in, his velocity in that reference frame in Vx prime is negative 80 kilometers per hour. So the truck is traveling, say the truck in the video was traveling, I think, to the left, right? But he's traveling at negative 80 kilometers per hour. So I have negative 80 kilometers per hour and 80 kilometers per hour. I add 80 kilometers per hour to both sides, and I get Vx is speed in the reference frame of the person standing on the side is 0. Okay? And so that's why he just drops straight down off the back of the truck instead of flying to the ground. Okay. So that works for Newtonian physics and the Galilean transformation. However, the relative speeds between frames approaches c. And so c is speed of light in a vacuum. Recall that c is equal to 1 over the square root of magnetic permeability times electric permittivity of a vacuum, then Newtonian relativity, which is what we've described so far, cannot work. And so I'll give you an example. Light does not obey Newtonian relativity. All right. So let me give you an example of what I mean by that on a slide. So this is Einstein's relativity. Instead of Newtonian relativity, we now need Einstein. So let's say that we have a spaceship that is capable of traveling at half the speed of light, and it's traveling to the right. And then I'm over here with a laser, and I fire this red laser towards the spaceship. Okay. Well, an observer in the frame of the red laser will measure its speed, its beam speed to be c. Now, Newtonian relativity would say that I fired the laser at c in this direction. The space traveler is traveling in the opposite direction at 25 c, and so you would think that they would see 1.5 c, because you're traveling along the interstate, you're driving at 60 miles per hour, there's cars coming in the opposite direction at 60 miles an hour. You see them traveling at 120 miles per hour from your perspective, right? But that's not the case with light. Okay. If I fire this laser at speed c in my reference frame, and this person traveling towards me at half the speed of light sees it also traveling at c. That's very strange, right? Traveler in the spaceship will also measure the red laser's beam speed to be c. So I gave you a piece of paper earlier today, right? Yeah. So she's holding up a piece of paper. Okay, so I'm going to use a little flashlight on my phone. Right. So how fast is that light traveling towards you? Okay, show it to everybody else, not to me. I don't need to see. Yeah. It's traveling at the speed of light in a vacuum. Now, okay, it's slightly slower than that because it's traveling through air. Okay. Now you ready? We're going to take another measurement. You can put it down. All right. So that was when I'm standing still relative to you. Okay. So now I'm going to run fast towards you. Now how fast is it traveling towards you? C. Exactly. Okay. All right. So thank you very much. So even if I'm running towards her with some velocity towards her, so now it should be c plus whatever speed I'm traveling towards her, right? It's not. It's still c. It's still the same. Okay? Now, you notice that I don't have any demonstrations in here today. Most of the time I bring in demonstrations. Today I don't have any demonstrations. That's my demonstration for today. Because, first of all, I know you were very impressed by how fast I ran. But I cannot demonstrate things where something, like a little, laser on a cart is traveling at near the speed of light. We can't do that in this lecture hall. There's other reasons why it's not possible, but it's very difficult to demonstrate this kind of setup, this kind of situation in physics. So that's why we don't have demonstrations today. But we can at least imagine a spacecraft traveling at half the speed of light and a laser beam traveling towards it, and they both measure c. Both observers measure c. How is this possible? Well, we need special relativity in order to describe this. So first postulate of special relativity. All laws of physics are the same in all inertial frames. Okay, no problem. Second postulate. speed of light in a vacuum is the same in all inertial frames independent of both the speed of the source of light and the speed of the observer. Okay. So this seems strange. All right, so I gave you two examples. One where we have a stationary laser and a spaceship traveling towards that laser at half the speed of light. Both observers, the person holding the laser and the person on the spaceship, measure the speed of light, the speed of the laser to be seen. And then we did the experiment in class, where we had a stationary observer and a moving light source, me running towards her with my phone flashlight on, right? And in both cases, regardless of the speed of the source of light or the speed of the observer, everybody agrees that the light is traveling at c, the speed of light in a vacuum. All right, so how can we make this work? How can we make this second postulate work? Well, we have to start messing with both space and time in order to do that. So let's start with time. We have to define proper time to begin with. And this gets a little bit confusing, so I want you to think about this carefully when we're describing this. Proper time is the time interval between two events that occur at the same place. So you're currently sitting in your seats, right? You probably were sitting in your seat at the beginning of class, you're probably sitting in the same seat at the end of class. I don't think anybody's changed seats, right? The amount of time that class is taken from when you sat down to when you get up is a proper time. Because those are two events in the two events that occur in the same at the same place. Or another way to describe this is that this is another way to describe proper time is the time interval measured by a clock at rest in that reference frame. All right, so let me show you an example of what we mean by that. So one way to build a clock is to have a laser, and you send a little laser pulse towards the mirror, and then the laser pulse comes back and hits your detector. So that's my light clock over here on the left, right? The laser shoots a pulse downwards towards the mirror shoots the pulse backwards, or reflects the pulse backwards up towards the detector, and I measure how long that takes, and it clicks, it starts the time when the laser is fired, it stops the time when the laser hits the detector. And say I measure 0.002 in some time units, I don't know, nanoseconds, whatever. And there's a distance between the laser and the mirror, d, okay? So that's my light clock. I have one on Earth. And I'm an observer on Earth where we're going to say that's our reference frame relative to the ground. V is equal to 0. Okay. Now let's say that there is a person in a spaceship, and I give them the exact same light clock that I have on Earth. So it has a laser and the distance between the laser and the mirror. It fires a laser towards the mirror. The laser reflects back up, and the detector measures how long it took from when the laser was fired to when it returns to the detector. Okay, so the observer on the spaceship sees the exact same thing that I saw on Earth. They see the laser go straight down. And by the way, they're on the spaceship traveling past Earth at 0.745 times the speed of light. Very fast. Okay? So they see from in their inertial frame, their reference frame, that's traveling at constant velocity to the right, they see the laser go down and come back up, and it takes 0.002 for them. Right? That's their proper time, just like it was our proper time in reference frame theory. However, the person on Earth does not see the laser travel along a straight path down and a straight path right back up, because the laser is traveling at c, speed of light in vacuum, for both observers, but the observer on the spaceship relative to the observer on Earth is also traveling at 0.745 c to the right. And so the observer on Earth sees the laser travel along a diagonal path, like this, down to the mirror. And because the mirror is traveling horizontally, right, in the time that it takes the laser to get downwards, right, it reflects off the mirror and it reflects back up, but the path that it is taking is longer from the perspective of the observer on Earth. So instead of traveling a distance that is just 2 times capital D, it travels along a path that looks like this V shape in red. And that is longer than 2 times D. And remember, for both observers, each laser has to travel at the speed of light c. And so, even though it's traveling at c in this V shape, it's traveling a longer distance, and so from the perspective of the person on Earth, it has to take longer. And so they see the person on Earth measures 0.003. They measure 50% longer than the person on the spaceship measures. Now this is the person on Earth watching that clock go by. Right? The person on the spaceship still measures 0.002. So they disagree about time. So this is different than the Galilean transformation, where you have a person driving by you in a car, looking at their watch, and you're looking at your watch, and you both agree on what time it is. Okay? This is different. The two observers don't agree on time. All right. The person on Earth is measuring time pass more slowly for the light clock on the spaceship, because the person on Earth is really measuring the amount of time that has passed between when the laser was fired and when it gets back to the detector as 0.003, but they only see 0.002 tick off on the clock. So they're saying that it takes 3 whatever for it to click off 2 times. So it's kind of like saying, well, a second has slowed to 1 second that I'm measuring from Earth looks like a second, I'm measuring, I see their second hand ticking, but instead of seeing the second hand tick and take 1 second to tick, it takes a second and a half for the second hand on the clock to tick by, from my perspective from Earth. Okay. Let me go over that for just a second again, right? So the person on the spaceship still sees the light clock measuring 0.002. The person on Earth sees 0.002 tick off on that clock, but using their light clock, they measure that taking 0.003. Okay? So if these were seconds, if it was tick, tick, right, they would see it as tick, tick, slower. Right? They would still see the same number of seconds tick off, but it would take longer from the perspective of the person on Earth. All right. And so that brings us to time dilation. Delta t is equal to delta t proper divided by the square root of 1 minus b squared over c squared. All right. So in this equation, delta t proper is the time difference for proper time. So the time difference for proper time, delta t proper, remember, we described that as the time interval measured by a clock at rest in that reference frame. So that's the person on the spaceship measures how much time has gone by for the laser to go from the laser to the mirror and then back to the detector. They measured 0.002. That's the proper time. Okay? This delta t is the time difference, in frame that's moving at v relative to the frame proper time. So this is how much time the person on Earth measures that 0.002 to have taken. And if you put in 0.745 times the speed of light into this speed v divided by c squared, 1 minus that, you take the square root, then you get a longer time, 0.003 over here. So that's the time measured by the person on Earth for how long it took the light clock on the spaceship to tick by 0.002. Okay, so the person on the spaceship measures 0.002, and the person on Earth looking at that clock says that that took that clock 0.003 to tick off 0.002. So time difference in the frame is moving at v relative to the frame of proper time. Now I know you're thinking, well, the person on Earth though is not moving at v. Well, they are relative to the spaceship. Remember, there's no absolute motion. So spaceship flying by at v, well, Earth is moving at v in the opposite direction. Okay. Since c is approximately 3 times 10 to the 8th meters per second, it's a very high speed, we don't usually observe time dilation. In day-to-day life. Because if v squared over c squared is very close to 0, which it is most of the time, say I'm walking across the room, I'm only going at about 2 meters per second, something like that, maybe 3 meters per second as I move across the room. Let's say I'm going at 3 meters per second as I walk across the room, right? 3 meters per second squared divided by 3 times 10 to the 8th meters per second squared gives me 1 over 1 to the 10 times 10 to the 16th. That's basically 0. And so then I have square root of 1 minus essentially 0 is 1. And so my time and your time are the same because my speed relative to you is not very fast. And even if I get into something very, very fast, like fighter jet traveling at a couple thousand miles per hour, right? That's still much slower than this. And so v squared over c squared is not going to be a very large number, and it's going to be very close to 0. And so this is proper time and delta t are going to be the same for basically everybody in day-to-day life. Okay. However, we can imagine that we can move at much greater speeds. So let me ask you a question about that. So we should open up learning catalysts. I know we're towards the end of class here. I want you to think carefully about this. I'm sorry, I didn't say how long I would give you. I'll give you just a minute and a half, so we've got about 30 seconds left. I want you to remember that there is no way to detect absolute motion. In inertial frames, let's put that. I'm giving you a little bit of extra time, so 15 more seconds. Does anyone want more time? Doesn't look like it. All right, so let's stop it there. Okay, correct answer is they both measure each other's clock ticking slower. So she measures his clock ticking slower, and he measures her clock ticking slower. How is that possible? It seems wrong, right? It seems like one of them should be right, but guess what? They're both right. Okay? So if he's traveling at half the speed of light, he will see her clock ticking slower. But he's only traveling at half the speed of light relative to Earth. From his perspective, Earth is traveling that way at half the speed of light. And so Earth has a clock that's ticking slower from his perspective, right? It doesn't matter. Neither one of them has absolute motion. We're just so used to, the Earth being our reference point that we don't think of things, moving. We don't think of the Earth as moving. But in this situation, there's both inertial frames, and it's symmetric. There's no difference. The only difference is I, gave them different names, and they're traveling on different objects. One's on Earth, and the other one on spaceship, right? But in terms of the actual physics of describing the situation, right? Well, one of them's moving to the right, from the perspective of that one, and the other one's moving to the left from the perspective of the other one. But otherwise, that's just a reflection. That's just a negative sign change in the equations. It doesn't change anything. They both measure the other one's clock, ticking slower. It seems strange. Now, what I'll say about this is that in order to, if this was a spaceship that had launched from Earth and then traveled up to half the speed of light, then that person on that spaceship would have had to have spent time in an accelerating non-inertial frame. And that means that their situations would not be the same. Okay? Right? And so for that particular situation, then it's not perfectly symmetric. And you would get different answers. And we're going to come back to that when we talk about something called the twin paradox. But before we get to that, we have to also mess with space. So we've messed with time, now we need to mess with space and do something called length contraction. So length contraction. So in the top train car is at rest, and it has a length, L rest. And Trillian, who's our person on the ground, I don't know if anybody's read the Hitchhiker's Guide to the Galaxy books, you may have recognized the names from that section. So Trillian's on the ground, and she measures the length of the train to be L rest, because she and the train are in the same inertial reference frame, v is equal to 0, right? Okay, now there's a different train car that is traveling past her at 8/10 of the speed of light, very, very fast. And now she measures that train car, and she measures that train car to be shorter, because it has been length contracted by this factor. L is equal to L rest times square root of 1 minus v squared over c squared. V is the speed of the train, so that's the speed of the reference frame relative to her inertial reference frame. And So she measures a shorter length. All right. Seems weird, but this is the way that works. Length contraction. An object traveling with velocity v will be shortened along the direction of v from the relative perspective of an observer at rest. So that's given by the equation that I had on that slide. L is equal to L rest times the square root of 1 minus v squared over c squared. So it's a very similar equation to the equation that we had for time. We have the same factor, square root of 1 minus v squared over c squared. But this time it's in the numerator instead of in the denominator. So that means instead of increasing the time, instead of delta proper becoming a longer time, this is now a factor that is less than 1 multiplied by L rest, so I'm going to get a shorter length. So L rest is the length of the object measured in the frame of the moving object. And then L is measured by an observer with v equal to 0. So again, if I have those two identical train cars, right, and Trillian is looking at one of them that's just sitting there, she measures L rest. And then the other one, which is the same train car, but is moving past her at some large fraction of the speed of light, she's going to measure a shorter length that will be contracted relative to what she sees. All right, let's go back to the slide for just a second. I have a question for you, but we don't have time for the question, so I'm going to save it for next time. But I just wanted to go back to this illustration of that. So these are the same train car. They have the same length for observers at rest in the frame of each car. So she's at rest in the frame of the car on the top. Let's say there's a person, a different person, traveling along in this train car that's traveling at 8/10 the speed of light relative to Trillian. Let's say it's Zaphod from before. He measures the length of the car, he's going to measure L rest because he's in that moving reference frame. He's in the reference frame of the train car. But from her perspective, the car is short because it's passing her by at close to the speed of light. All right, that's it for today. We'll give you an extra bonus minutes. We'll come back and talk about length contraction and the twin paradigm.